This video is talking about the development and current status of error-correcting code and explaining why 5G is collapsing and 6G is on the way to the future. The first part provides scientific knowledge to related entry-level researchers. The second part presents discussions and challenges for related theorists and product developers, as well as engineers engaged in implementation. The third part demonstrates 5G issues, WuShengHan coding family and future 6G ECC. The slide's content provides a viewpoint of the communication quality built by physical layer design. As we know, 3G, 4G, 5G, even 6G is worldwide wireless communication in the global. Then, let's think about how to build up low-level communication. We simplified the communication system into two parts, transmission side, TX, and receiver side, RX. The workflow is that the TX side intends to give some messages and send to others. The messages would pass through the antenna and arrive at the RX side. The RX side would try to get back messages from these. The question is how the RX side is able to recover TX's message without any miss. The answer is by the rules of digital bits, which are checking messages and indicating error locations at most. The rules are constructed before the communication starts. Mostly, specifications define these. The checking rules are also named error-correcting codes, the same as forward error correction. Let's ECC or FEC in short. The checking rules in the early system are based on polynomials. The system views messages as coefficients in polynomials, and order in polynomials is timestamp. Then the multiplication of message polynomial and predefined polynomial is the encoding process. In the RX sides, the remainder from received polynomials divided by predefined polynomials gives hints of error existence and locations. This was ECC techniques in the early system. The prior art introduces a concept, that is, adding redundancy as the basis for checking rules, and checking the remainder divided by common polynomials above is the use of redundancy. The decoding process is to use the remainder conversion mapping to the error position. Over time, researchers are involved with algebraic distance, graph theory merging into ECC development. The concept of distance is quite easy to understand, because the message sent by the TX-RX end is regarded as a vector, and the error caused by the channel is offset by the short distance vector of the old and new vectors, and the decoding process is to find the solution to the nearest vector problem. Graph theory about path is applied to how to generate redundant information according to the predefined ratio, and encode the information bits into the expression form of the finite state machine. During the decoding flow, the sequential searching of path costs by current state and the next state can deduce processing of the decoder inferring information bits with the maximal likelihoods as indication of the nearest distance. Inserting redundancy will lengthen the trellis distance in the state machine if errors are injected. Graph theory intuitively proves that the maximum likelihood yields the decoding results of the nearest vectors. Furthermore, soft decoding enhances high resolution of the computing distance, which is beneficial for expressing the probability of the nearest vector. For specific mathematical details, please refer to the algorithm and theory of convolutional code with Viterbi decoding. It is worth mentioning that the Viterbi decoding does not always give the best results for any code construction. As an example of identifying items, if you are 1 kilometer away from your neighbor, you can distinguish your belongings from your neighbors in a simple way. In contrast, if you are only 1 meter away from your neighbor, even with property markings and various preparations, it always tends to misidentify belongings. Decoding processing is how to identify belongings, and code construction is the distance of these things. In addition to discussing a single decoder, the topic is also gradually whether combining or concatenating decoders can bring different effects. For example, convolutional code plus Reed-Solomon code is fighting against two types of error events. The above paragraphs describe redundancy, polynomials, state machines, soft decoding, the application of distance to graph theory, and other parts not mentioned, providing a practical basis for this ECC study, and they express a clear description and implementation. It is convenient to design the inspection mechanism required by the product, and simply change different parameters to meet the requirements. The next decade saw no progress in the field. Coding is dead is a slogan that was popular among this research around 1980. The turning point of the matter was the discussion of turbo code in the standard formulation of 3G WCDMA in 1993. What is turbo code? In the discussion at that time, no engineers and designers knew about it except those from France. Let's briefly describe the encoding process. The same information stream generates highly irrelevant redundancy by using the interlavers forward and backward. The corresponding is to use irrelevant redundancy to decode ping-pong streams. This corresponding decoding introduced several cutting-edge concepts, like combining extrinsic message exchange with interleaver and iterative decoding. The idea is an improvement that originated from the concatenated code in the earlier part. The iterative concept is simple, that is, reuse the decoder and lets output closer to the possible results multiple times if convergent conditions do not meet. The interleaver concatenates the info streams. Even its novelty of extrinsic message exchange took a long time for scholars at the time to discuss, explain, and accept its superiority over the traditional techniques. The question is how to create useful input information to make it work instead of wasting resources. The decoded original information stream has part of which is replaced by the recorresponding order of the forward and reverse interleaver. Another critical point is that the latter input needs to remove the influence of the previous input before starting the latter decoding. This step removes the information accumulation of iterative decoding, and experiments confirm the necessity of this removal. The next output is generated from the source of the original TXRX end and the source of the previous time. Remember to remove the influence of the current input before decoding. As shown in the figure, these iterations achieve an amazing error-correcting effect. But some corresponding side effects are also induced. The biggest side effects can be categorized into two effects of lack of process predictability and unknown error tolerance. The predictability of the process is blocked by adding the interleaver. Interleaver can bring independent and quasi-random effects, disperse the correct results of the convolutional code to achieve positive feedback, but the randomness is unpredictable. Although convolutional code has a rigorous mathematical upper bound, adding the interleaver ruins its guarantee and effectiveness. This ruinness of guarantee causes an unsmooth curve in the error description figure. This is called an error floor, and it means that multiple error reductions do not give an exponential gain to the output. In other words, a fairly low error scheme will still fail the decoder. In contrast to the early techniques, a guaranteed process does not suffer from this disadvantage. Keep the conclusions in mind at this stage. LDPC is back on the stage in the wave of turbo code. It was proposed in 1963, but also lacked a favorable description to compare with contemporary technology and was buried for more than 2 decades. Among the criteria that turbo code has, the LDPC code is also specifically implemented. The following side effects are also similar, which is an indescribable error floor. Let me introduce the details of LDPC code. The LDPC code is defined by a matrix, of which the entries are binary values as 0 and 1, called parity matrix. The messages of TXRX are regarded as vector streams. So the checking actions are matrix vector operations. The checking operations take effect by location of ones in the parity matrix. The reason why the code is named as low density is that the ratio of 1 versus 0 is quite sparse. The result of matrix multiplication by vector can be used to guess the existence of errors and how to correct them. Compared with the previous technique, the form of polynomial, state machine and graph theory can be efficiently converted into matrix representation. Modern understanding and discussion of matrices inspired the advancement of ECC technology. Of course, there are still unsolved mysteries. What it can't explain effectively in the first place is how to define sparsity of ones and how to properly arrange ones. The pseudorandom method can evenly mix the information of Rx, which also brings difficulties to the implementation discussion. Each designer deduces future worthwhile research based on distinct experience. We expected the uncorrectable probability from TXRX is as small as possible. So over time, various published papers and simulations have gradually advanced the correction capability and improved the error tolerance of Rx reception. However, there is no unified standard, the progress is merely judged from different subjective angles. Because randomness is hardly described by mathematical formulas, the description of correcting capability can only be simulated by computers. The observation of powerful capability takes lengthy simulation time and each participant's resources for long-time engagement that depends on different man's patience. The performance presented by each designer expressed results with relatively small numbers, and bystanders did not have any difference in perception of small numbers, causing confusion and misunderstanding competition. That finally affected the quality of the TXRX system's fault tolerance. Chaotic, unreasonable competition for correction capabilities make the current situation a process of retrogression. This gaming competition is one of the main points I want to describe in this video. The next video will explain the details of chaotic and unreasonable. What is the failure rate we will be satisfied with this type of TXRX communication system? Is it enough to fail one during 1,000 trials, or 1,000,000 trials? At this time, we will discuss the concept of infinitesimal in mathematics, a number that is not zero but relatively few meaning wasting parts of the system resource. The expectation for the failure rate should be as small as possible but not zero. For people, 0.0001 may be very small, and ppm, parts per million, or ppb is usually used in product engineering. For the failure rate of the TXRX system, it needs to distinguish the failure rate of the probability of 1 times 10 to the power of -4 and 1 times 10 to the power of -7 to meet the growing higher speed system. Even in utmost quality, what does the failure rate of 1 times 10 to the power of -9 mean? You can compare the quality of wired communication here. At this time I would like to introduce a clearer formula to describe. The number of failures per unit time is equal to the system throughput times the probability of uncorrectable failures. The typical throughput brought into the application is 10 megabytes per second, if the vector of TXRX is roughly 1000 bits with volumes about 80,000 TXRX vectors sent and received per second. What is the difference between 1 times 10 to the power of -4 and 1 times 10 to the power of -7 of an uncorrectable failure rate? The former will have an uncorrectable event between 0.12 seconds, while the latter interval is about 120 seconds, 2 minutes. The viewers of the video can speculate that if we increase the transfer rate to 100 megabytes per second or 1000 megabytes per second, what is the interval between failure? At a speed of 1000 megabytes per second, the system requires a lower error rate than 1 times 10 to the power of -9, because the user does not want a shorter uncorrectable interval and often encounters failure events, affecting the latency by instability. What is the concept of testing 1 times 10 to the power of -4, 1 times 10 to the power of -7 until 1 times 10 to the power of -9? The error rate of 1 times 10 to the power of -4 is approximately 1 failure in 10,000 attempts. Out of 100,000 attempts, about 10 failed, maybe 7 or 8, maybe 12 or 13. Probably the designer has a foreknowledge that if the result is 1 times 10 to the power of -4, the test volume will probably be 30,000 to 200,000. This test volume depends on the designer's patience. With current computers, these attempts are about a minute or so, and this is a relatively simple cost. What about the estimated result of 1 times 10 to the power of -7? The difference is 1 times 10 cubed times, which is 1000 times. What is the 1 times 10 cubed concept? The cost of 1 minute of testing becomes 1000 minutes, about 16 hours. It is lucky to get the expected result after 16 hours. Please feel difference. Let me elaborate on this difference from 1 times 10 to the power of -4 to 1 times 10 to the power of -7. Oftentimes this is not the case. More of this testing process won't be done just once. If the result is worse, then the time lapse after the debug process has to be done again. It is very possible to change the setting, or it may be done again due to human misfortune. In addition, it may be that the expected result of 1 times 10 to the power of -7 is 1 times 10 to the power of -6, and the candidate needs to change the parity matrix again, then it is necessary to try dozens and hundreds of matrix candidates one by one after testing and selecting. If a potentially suitable candidate is selected and the sensitivity to decoding is further tested with other settings, large error rate fluctuations due to reliance on unreasonable soft decoding may be uncovered. I was so sorry to say, discard this and move forward to test the next. After going through a full process, for a multi-length ECC family, you need to examine every ECC mode. Maybe parallel processing can speed up testing, but 20 or more sets of long-term simulations at the same time is tedious and tiring work. The ECC coding quality depends on the patience of the designer. Most players did it by lowering the verification criteria. When someone wants to improve quality verification, they are faced with the current market situation where bad money drives out good. How does the TXRX system rescue when stuck by uncorrectable events? That is, if ECC with a higher uncorrectable rate, the step of slowing down is inevitable. If we increase the throughput of the new system design by several times, the corresponding failure rate must be reduced by several times to resolve the failure immediately. From the application's point of view, what is the ECC failure rate of the 6G system to meet the application? At least, I think it must be lower than 1 times 10 to the power of -8. From a testing perspective, how long and how many test cases does the system have to go through for qualification in stage specification definition? Some researchers will say, the system has other remedies, the system will not simply crash. At this time, it is necessary to remind that if the first stage decoding is invalid, after the second or more measures, the system may recover the data, but it has slowed down. Reception quality can be improved by fine-tuning the channel conditions, for example. Increase the signal-to-noise ratio to reduce errors. In the same situation, just changing to a better ECC decoder will improve the fault tolerance rate. Therefore, the adjustment of the environment and the discussion of ECC quality are two unrelated topics. By description of conditional probability. The probability of error bits from TXRX multiplying the probability of UECC based on error bits is equal to the probability of UECC. The first item represents that environment performance has nothing to do with ECC. The second term represents the correction capability of ECC in the event of various erroneous bits. Get the failure probability of the uncorrectable events to express the TXRX quality. Keep in mind that systems with primitive higher uncorrectable rates cannot support industrial applications like self-driving cars, nor low-latency support for sophisticated telemedicine applications, and so on. Correction capability is a priority topic for ECC discussions, and the next step is to discuss multi-mode to select different lengths for various requirements. Faced with the same scheme, since the mathematical description of the random construction cannot be accurately provided, it is necessary to conduct a long simulation of all modes. Now let's take a guess. To what extent was ECC technology first discussed in 2017? After the discussion of the second edition of the 3GPP 5G standard, what is the update of ECC and how to strengthen the error correction capability? The answer is behind. After discussing each mode, the system needs to implement compatible design with low complexity. The merits of low complexity benefits low power consumption, and specifically we compete with energy efficiency unit throughput per unit cost. So how do we analyze complexity? The analysis of the LDPC code is relatively simple, just check the content of parity matrix. Because the ones in the matrix take effect in processing data, the number of ones and their location are highly related to the complexity. At this time, some researchers will say that the number of ones decreases, although the complexity is low, it will affect the correction ability, and it has better use more ones. This is a wrong statement. The number of entries in the matrix is more than tens of thousands, and the permutations and combinations of about thousands of ones are filled in. Generate a matrix with multiple combinations, A equals 10,000, B equals 1,000, to verify the quality of the capability. At present only by the simulation without a mathematical description, nothing cannot be obtained even in hundreds of years. The wrong conclusion, the reduction in the number of ones will affect the ability to correct, is misleading the public. In real-world, applications only need to pick one optimal solution among many candidate matrices. We don't care about the average performance of the matrix across all combinations. In other words, we don't discuss the general case and just choose the top one. The wrong direction, the number of ones will affect the correction ability, reflects the unnecessary cost due to insufficient the designer's strength. Conversely, the best matrix candidate equipped with the lowest cost is validated correctly under stress tests to obtain the highest quality of error correction. Be careful. All modes in each TXRX case take a long time to clarify each infinitesimal with tedious competition. And the mode patterns must be similar in a pseudorandom arrangement to achieve low complexity. Therefore, code construction requires superb skills and precise methodology. Later I will report the results of my implementation of high-quality low-complexity coding family. Next, let me explain the conclusions of some previous studies. Older techniques including exit chart, stopping set, absorbing set, important sampling can efficiently shorten test time for checking LDPC. I am suspicious about these detection solutions. Because the problem with ECC is that the very low probability of failure occurs on very rare point-to-point connections. And these detection solutions cannot tell whether there is an exhaustive and very complete set description or inspection of the matrix. Once the missing and unconsidered corner events lead to inaccurate conclusions, it is misleading to do such a flawed analysis. Next, explain whether there is AI to help LDPC become better. Personally, I think that the level of accuracy caused by AI's identification method is different from the 1 × 10⁻⁹ or lower range of ECC's excellence. It is difficult to correctly guide the error correction method of 1 × 10⁻⁹ with a high miss rate of 1 × 10⁻⁻². I think ECC comparison is an easily misunderstood process. How to come up with first place is similar to the idea of how an athlete moves towards a world record. If placed in the final application, it can be integrated into the overall solution to improve fault tolerance at most. Therefore, a key point of extreme testing is under hard decoding to compare correction capabilities, which applies to all error correction solutions and is a fair competition. Soft decoding has been introduced historically because it brings attractive results but relatively increases the test cost. Now we know that every ECC decoding has soft decoding, so nothing special. The soft and hard decoding has nothing to do with the minimum distance. There is no need to argue about how to sample soft decoding. The decoding flow does not affect the content of the matrix. Just like the superhero sparring in the movie, taking off the suits and competing with each other is a reasonable test. Remove soft decoding and restore to hard decoding, which helps to speed up testing and concluding early. If the resource is you can use the lowest bit decoding x 2-bit LLR calculation. So how do we discuss other conditions for limited testing? Because you are looking for a computer-aided parity matrix, you must have an error floor. I use algebraic properties, so my design is better. For other designers, they will still make such label-style comments. The judgment of things is based on their appearance, their paper with high error rate figures, and their weak math formulas without industrial testing to comment on. And they do not test hard decoding, and always skip the limit test. There are many such researchers with these misleading ideas. Shows only masking results. No matter what you do, you must have an error floor. What is the error rate under what conditions in the history line to see the event of the error floor? If hard decoding is used to achieve more than 10 times 10 to the power of -8 or lower, is the past experience using the same criteria? Remove the soft decoding and only mark the hard decoding. Who said error floor in this condition? It is easy to mislead bystanders to draw blurred conclusions. Some people will say, there is a gap between the displayed results and the actual results. As far as I can tell, it feels like in the testing and review phase, all modes are not clearly visible. And the designer chose a better mode and pretended that all modes had the same performance for the reviewer. As mentioned above, the pseudo-random character of the result is difficult to relate to its quality, but can be clearly reviewed by simulation. None of them can be ignored by long simulations if the application requires them. In addition to knowing the results, you should also be concerned with consistent non-relaxation test conditions. Some people say, there is polar code to replace LDPC. If you have an understanding of the test methodology above, you will want to know what is its hard decoding for polar code. I have sent a letter to the author, but he is still avoiding the discussion of error floor verification. Remember that hard decoding works for all ECC coding. And the results of the stress test about polar code will fail. There are too many opinions to say, and I will talk in the future. A simple conclusion is: please pay attention to the description of the objective conditions of the TXRX parameters, the same comparing configuration, and at least 1 week patient with the FPGA simulation providing the order of magnitude to reach 100 TB and to judge their quality. Remember to watch out that the y-axis is frame error rate or bit error rate. Avoid comparing oranges with apples before jumping to a conclusion. Also avoid using only 1 or 2 curves to judge whether it is good or bad. Look at the actual written records and reasonable time to double confirm. Wouldn't it be nice to stress test with a relatively limited decoder and get super good results? Let's go back to 5G. Why does 5G fail in ECC parts? Let's take a look at the chairman's summary. One question is the number in the y-axis to 1 times 10 to the power of -3. There are similar figures about LDPC in the form of BG1 and BG2 and polar code. Was it ready for a high-speed future? Yeah. This was for the 5G system in 2016 to 2017 discussions. Nothing improved after that. Push stop button if you need to see it clearly. The second question is its flexibility, how to meet different lengths among all modes. Its idea uses lift size to change the size of the matrix. Such problems can make digital design complex. Design multiple similar barrel shifters and mucks to make placement and routing complicated. My suggestion is to use a fixed one, such as the QC_size variable I define to the power of 2, such as simply 64 or 128, and then design different lengths as multiples of QC_size without changing QC_size. The design process is using fixed size floor tiles at the floor plan stage. The third question is length design. My proposal is that the system should design the length in binary notation. Using binary representation to change the complexity of O, log, the easiest way to reduce the design. Finally, through my work promotion at Final Page, you can know what is the best ECC design at this stage. The previous description only mentions 5G, and there are many standards that integrate LDPC into modern applications, such as TV video, DVB, and CCSDS. For example, ECC on Wi-Fi used convolutional code was integrated into LDPC code in 802.11 AC, but still is set as non-mandatory ECC. Why? Its early design drives the high-cost decoder, but it did not guarantee error cleanability. Recently, Wi-Fi 7 still seems to have no discussion on the error floor and a better one. One of the most direct scenes, from a computer on one end to the display on the other end through Wi-Fi, the unbuffered TXRX directly feels the response time of both ends and the flicking screen. Even the low distance and low error transmission cannot be displayed smoothly on the screen for a long time. You can try it. Look at the application of 10G Ethernet T in the network layer using RS-LDPC. This is an algebraic label indicating that it seems reliable, but lacks flexibility. Currently, the 100G to 400G Ethernet of the higher speed network connection layer will return to utilize RS code. Why? The history of LDPC in WiMAX development, the ECC itself has a lot of disagreement, and the cost of hardware design is high for all settings. At the same time, the construction of LTE specification directly skips LDPC and goes back to turbo code. So, the following will provide 6G reminders. Let's see my work about WSH coding family. One feature is its encoder with double quasi-cyclic form. The DQC matrix provides its inverse matrix with the same form that is saving memory size of ROM for each parity matrix. Just store one vector and double circularly shift the vector to complete encoding flow. If compared with old techniques, the triangular matrix is too complex and not elegant. The length of WSH encoding is selected as a power of 2, which is convenient for the input binary number length. The parity of the WSH ECC selects a fixed interval to match different power of 2 lengths and to meet the error rate of different input channels, finally forming a beautiful curve group. WSH ECC is selected under stress tests. And following the hard decoding comparison, it will follow BCHT value over uncorrectable rate under 1 times 10 to the power of -8. All are done by hard decoding comparison, and are drawn curves again by 1-bit soft decoding. The implementation of the WSH coding family is based on the degree 4 parity matrix, which guarantees the simplest complexity for all modes in WSH coding. The QC size fixed by all modes is 64, 2 of power 6 that achieved 1 GBs encoding by x86 CPU. And the parallel processing of decoding could be 64, 128, or 192 bits that achieved over 100 Gbps throughput in 1 GHz clock. At most the hardware with 192 bits processing cost less than 650K logic gates. This is almost 40% off and quite efficient than any advanced system such as 5G. The noticeable difference is the decoder implemented by column shuffle architecture. In a mode-changing scheme, the decade ratio of throughput is proportional to the ratio of length, not parity size. It is easy if the system needs a hard scheme. If you want to know more details, please contact me. What is noticeable in 6G? A poor ECC will waste more time rescuing data, causing a huge gap between the system evaluation and the final result. A poor ECC will be more complicated and lead to difficult routing congestion and IR drop in the later stage. A better system needs design simplicity but not more adjustment methods. Following the 5G criteria is to build another 5G system. Please avoid a death spiral caused by poor design like 5G. The understanding of zero-knowledge proof is beneficial to 6G validation. We must think about how to discuss rationally and make accurate choices for high-speed 6G.